Welcome students to my sixth lecture of Control System 2. In the last lecture we have discussed with several examples how to represent a dynamical system using state space representation. We have taken the example of electrical network, which is a MIMO system, and also we have taken the example of a mechanical system where we have seen that two masses are connected with the spring and the damper, and how the system is represented using state space representation, that also we have seen. Today we are going to discuss some other examples to represent the systems in state space. So as a first example we are taking electromechanical system, where we can see that an armature controlled separately excited DC motor has been taken, which is rotating which is driving a rotational load with a resistive load torque TL. So let us try to identify several parameters and variables associated with this electromechanical system. So the armature resistance, inductance and current are denoted by RA, LA and IA. EB denotes the back electromotive force, and TM is the motor torque. So here you can see RA, LA and EB, and the IA is the current flowing in the armature circuit. Tm is the motor torque, and now theta and omega, the motor shaft angular position and velocity. So theta and omega. So theta is the angular position and omega is the angular velocity. And J and B, the moment of inertia of the load and the viscous damping constant. So J is the moment of inertia of the load and B is the viscous damping constant. TL is the load torque disturbance. So TL, what it is working here, additional load, you can say that is that you can think that it is a disturbance to the system. Now from the motor equation we know that the motor torque is proportional to the armature current IA. So that's why the first 48A equation has been written, Tm equal to KT into IA. And EB, the back EMF, is proportional to the angular velocity of the shaft. So EB equal to KB into omega, where KT and KB are the constant provided by the manufacturer. Then we will write the system equation by summing voltages around the loop, that is the electrical balance we will write, and some of the mechanical torques resulting in acceleration, that is called mechanical balance. So here if we want to understand what are the inputs to the system, here here the single input is present, that is the armature voltage U. Okay, and if we want to know what are the positions of the what are the outputs of the system, you can consider the angular position of the shaft and the angular velocity of the shaft. So this could be the position, means this could be the output of the system. Now the question is what will be the what are the variables will qualify as a state variables. So even if you are not able to decide by looking the system, but if you write the dynamics of the system using basic laws, from there also you can understand that the variables who will qualify as a state variables. Let us do that, and from there only we can understand that what are the variables will qualify as a state variable in this system. So to do that one, first we will apply the KVL in the electrical loop. Here the field, it is actually armature control, so the field current, whatever the field current is flowing, that we will consider as a fixed. Now if we apply the KVL in this armature loop, then easily we can see that U, that is armature voltage, will be equal to RA into IA plus LA into DIA by DT plus EB we can write. So let us see the first dynamical equation we will get by applying the electrical balance. So using U equal to RA into IA plus LA into DIA by DT plus EB. And now, just now we have understood that the EB, the back EMF, is equal to KB into omega. So we will replace that value, and we have written the LA into di by dt is minus KB into omega minus RA into IA plus U. Now from this equation, actually one hint has been given that which variable will qualify as a state variable. We know that always in a system, if some variable is a state variable, then definitely its derivative is associated with it. So that's why you see we have written dIA by dt. So definitely from here it is clear one of the state variable will be the IA, that is armature current. So now second, we will move, after identifying the first differential equation, we will move to write the mechanical balance. So first differential equation, if we see the mechanical balance, that is d theta by dt will be omega. So here you see another hint to choose the state variable. D theta by dt is equal to omega. It means that here one first order differential equation is associated with the theta variable. So d theta by dt is equal to omega. So definitely theta will qualify is another state variable. Now we will write the torque equation. So if you write the torque balance equation, that is Tm equal to TL plus B theta dot plus j theta double dot. So now we are writing j theta double dot is equal to minus b theta dot plus kt into Ia minus TL. Now you are finding that this is a second order differential equation. Now already we have assumed that d theta by dt is equal to omega, means theta is a state variable. So now if we want to take another state variable from this differential equation, that is 51, because we have to convert the 51 as a two number of state variables. How we can do that one? Now if already we have assumed that d theta by dt is equal to omega, then if we want to write that d omega by dt, what will be that? That is basically we are telling that theta double dot, and theta double dot can be written from the equation 51. So it means that omega could be another state variable. So already you see in this network or in this system we have identified three state variable, Ia, theta and omega. So even if you are beforehand not able to decide for a given system what could be the state variables, better you can proceed to write the differential equations, and from there it will be easy for you to decide that which variable will be is going to qualify as a state variables. Always the hint is that you have to see that which variables first order differential equations are associated with the dynamics of the system, and that variable whose first order derivative you are writing will qualify as a state variable. And as we have seen that the system output could be the angular position of the shaft and the angular velocity of the shaft. So y1 and y2 are the two output, and we will now give the name of these chosen state variables, that is x1 is equal to theta and x2 is equal to omega and x3 is equal to Ia. Then after assuming the state variables theta, omega and Ia, now we have to transform the equation 49, 50 and 51 with the help of the defined state variable x1, x2 and x3, which is very easy to write. Suppose first 49 if we want to write with the state variable, first if you will take the equation number 50, because we have assumed x1 equal to theta. So what we can write, x1 is equal to x2, because x1 dot means what? Theta dot, and theta dot means what? Omega, and omega is represented by x2. So x1 dot is equal to x2. So now the right hand side, as I told you, that always it will be the function of states and input. So we can write this one 0 into x1 plus 1 into x2 plus 0 into u plus 0 into TL. Here TL, we are assuming that the torque which is also working or also present in the system, which is working as a disturbance input. Now the second equation we will write x2 dot. So if we want to write the x2 dot, which means that omega dot, and if you are writing the x2 dot, it means that you are writing omega dot. And what is omega dot? Omega dot, basically it is theta double dot. So now theta double dot, in which equation it is associated? The theta double dot is associated with the equation 51. So theta double dot we will write, means x2 dot we will write, that is 0 into x1 minus b by j into x2 plus minus kt by j into x3, plus there is no term associated with the armature voltage, so 0 into u, but there is a term with the TL, so it is 1 by j minus 1 by j into TL. Now we will write the last equation, that is dx3 by dt. So that is basically the dia by dt, which can be written from the equation number 49, and which will be the x3 dot is equal to 0 into x1 minus kp into la into x2 minus ra by la into x3 plus 1 by la into u plus 0 into TL. So once you have written the state equation, then you can write this state equation in a vector matrix notation, and we have output y1 equal to x1, that is the angular position, another output is y2, that is x2, which is the angular velocity. So now once we have defined the state equation and output equation, the next step to write the state space representation in vector matrix notation, which is represented by 55, and first part of the 55 is representing the state equation, and second part is representing the output equation. Here we have actually two inputs. One input is the desired input, that is u, another input is a disturbance TL, which is undesired for us, but still we can represent the system as a MIMO system, or we can see that two inputs are there, that is u and TL, and two outputs are there, y1 and y2, but there is no D matrix. Why? Because the outputs are not influenced by the input directly, so that's why the D matrix is 0. So in this way, another MIMO system, which is a separately excited DC motor, can be represented using state space representation. We will quickly move another representation, that is of a two tank system, which is a interactive tank. So now for this system, you can see that consider a liquid level system shown in figure. In this figure, the Q1 dot Q1 bar, so this is the Q1 bar, and Q2 bar are the steady state inflow rates, and H1 and H2 are the steady state heads or level. The quantities, that is QI1, so this is the QI1, QI2, H1, H2, then Q1, Q0, so this is the Q1 and this is the Q0, are considered small. Obtain a state space representation for the system when H1 and H2 are the outputs and QI1 and QI2 are the inputs. So here two inflow rates are given, but all the steady state values are given, that is Q1 bar, Q2 bar, H1 bar, and H2 bar, and now these small quantities are representing the deviation from the state variables. And for this system, it has been written that H1 and H2, the levels inside the tanks, are to be considered as an output, and two inflow rates, that is QI1 and QI2, which is instantaneous, these are the inputs to the system. But here in this system, no state variables are defined. So same thing, if you are not able to identify what will be the state variables for the given system, I will advise you to write the differential equation associated with this system, and from there you can decide that which variable will qualify as a state variable. So let us move to write the differential equation associated with this system. Before that, we have to relate some of the variables in this network or two tank system. That is, what will be the resistance R1 and what will be the resistance R2, how they are related with the variables H1, H2 and the inflow rates, how they are related. So to do that one, we will consider that the variation of the variables from their respective steady state values are small. The resistance R1 stays constant. Hence, in steady state, we can write Q1 bar. That is, you see the flow Q1 bar through the resistance R1 or valve R1 is represented is equal to H1 minus H2 by R1. How it has happened? Now H1 minus H2 are the potential difference here, and once we know the potential difference, then easily we can write the flow Q1 bar will be the potential difference by the resistance R1. So now this is the quantity has been defined for the Q1 bar. So now in this situation, when the system is in steady state, if there is a small deviation from the steady state Q1 bar, that is Q1 bar plus QI1, then what will happen? Then height H1 bar is to be increased by H1. So now the height will be the H1 bar plus H1, and definitely the outflow rate through the R1 is also going to be increased by a amount Q1. So now the new flow is Q1 bar plus Q1. So in this situation, how the relation of the variables will exist? So now we can write Q1 bar plus Q1 is equal to the new potential difference. What is the new potential difference? The H1 plus H1 minus H2 plus H2. So now from here we are finding that we can write H1 minus H2 by R1 plus H1 minus H2 by R1. So just now we have defined H1 minus H2 by Q1 bar. So now what will happen? This and this is going to be cancelled. So now we are finding that Q1 is equal to H1 minus H2 by R1. So this is the important relation. We are finding that the outflow rate through the resistance R1 is defined by equation 58. Now similarly, if we want to write for the Q0, what we can write? So Q0, we are finding that the potential difference is defined by H2 and the resistance is R2. So Q0 will be simply H2 by R2. So that has been written in the next equation 59, that is Q0 is equal to H2 by R2. H2 by R2. Now after knowing this two variables 58 and 59, now we will move to write the differential equation for this system. So which law we will apply to find out the differential equation for this system? Definitely the mass balance equation we will try to write. Sorry. So now for this two tank system we are writing the mass balance equation. What is mass balance equation? The mass flow in minus mass flow out is equal to rate of change of the accumulation of mass inside the tank. So we will write the we will apply this mass balance equation in the tank 1 first. So here the QI1 and Q, all the flows are in written in terms of volumetric flows. Means in SI unit we can say that their unit is meter cube per second. Fine. So now if we know that the liquid inside the tank having the density rho, then what will be the mass flow? Mass flow will be rho into qi1. Rho into qi1. How? Now rho, you know that the in SI unit it is kg per meter cube, and qi1 I told that it is a volumetric flow, so it will be meter cube per second. So ultimately this quantity rho into qi1 is telling you that the mass flow, that is kg per meter. So similarly we can see that from the tank 1 the outflow rate is that is rho into small q1, that will be equal to rate of change of the accumulation of the mass. So how much mass is accumulated inside the tank? The d dt of rho into v. V is the volume of the tank, and volume is represented by A1 into H1. A1 is the cross-sectional area of the tank and H1 is the instantaneous height. So now the rho is constant, so rho will be cancelled out, and ultimately for the tank 1 you are finding that the differential equation we are getting A1 into dH1 by dt is equal to QI1 minus Q1. So from this equation, from this equation, the equation 61 can be written. How? Now we know that the capacity of the tank is the cross-sectional area, so that's why A1 is replaced by its capacity, that is C1 into dH1 by dt is equal to QI1 minus Q1. Now this is the hint to choose the state variable. So now you see at any moment of time for a given input QI1, if you want to know what is the level inside the tank, so definitely you have to know what was the initial level inside the tank, that is H10. So definitely we can say that H1 will qualify as a state variable. Similarly for the tank 2, if you want to write, that is C into dH2 by dt is equal to inflow. What are the inflow rates? That is QI2 plus Q1, and what is the outflow? That is Q0. So it will be QI2 plus Q1 minus Q0. So dH2 by dt, C1 dH2 by dt, sorry, C2 dH2 by dt is equal to Q1 plus QI2 minus Q0, and from here it is clear that we have written the first order derivative of H2, so definitely H2 will qualify as a state variable. So now if H1 and H2 will qualify as a state variable, and in formulation already written that QI1 and QI2 are the inputs, then if you see this 61 and 62 very closely, right hand side you will find that the right hand side must be the function of states and input only, but H1 and H2 are the states and QI1 and QI2 are the input. But you can see that the QI1 is present, but another variable is present, Q1, which is neither the state variables nor the inputs. So now you have to think that how the Q1 can be replaced in terms of state variable and inputs. So now already you see, that's why we have quantified Q1 in terms of H1, H2 and the system parameter, that is R1. Similarly, if you see the equation number 62, here you can see that at right hand side that input is present QI2, but another two variables are present, that is Q1 and Q0. They are neither state variable nor the input. So now we have to replace the Q1, Q0 by the state variables, system parameters or input. So now we have written the equation that is for Q0, that is H2 by R2. Now you see it is the function of state variable H2. So now our work will be in the next, that to replace this Q1 Q0 from the equation 61 and 62 with the relation 58 and 59. So if you replace it, you are getting the first differential equation, that is dx1 by dt, by assuming here the x1 is equal to h1 we have written, and at the right hand side you can see that all mm, the terms are associated with x1, x2 and the input u1. Okay, here we have assumed that qi1 is u1. So here you see u1 is equal to qi1, u2 is equal to qi2, x1 is equal to h1, x2 is equal to h2, and the outputs are y1 equal to x1, y2 equal to x2. They are the height of the tank. Okay, so here you can see that measurable state variables can be the output. So here the state variable what you have chosen, that is h1 and h2, they are the outputs of the system. So sometimes it has been asked that is it always possible to choose the state variable of a system which having a physical meaning? The answer is no. It can happen that some variable will choose as a state variable which do not have any physical meaning. Maybe in the next example I will explain that one. So after assuming that is x1 is equal to h1 and x2 equal to h2, we have written dx1 by dt, that is 63, and we have written the another equation dx2 by dt, and right hand side you see all the terms are x1, x2 and u2, because here we have replaced the q1 and q0 with their relations, and similarly to get the dx1 by dt we have replaced the q1 by this relation. Okay, so now once you will get the 63 and 64 which is representing the state equation, we can write the state variable representation for the given system, and we can see that it is also a MIMO system because two inputs are there. They are the two inflow rates, that is u1 and u2, and the outputs here actually you should write y is correct, but y having a two components, basically y1 and y2, so that has to be written. So now y1 y2, that is the output of the system, can be written like this. So this is the state space model of the given system, which is a interactive tank. So you see, now we are quite comfortable that if a system is given, then how we can write the state space representation. So now again I am recollecting the things that any linear time invariant system, all the cases you will find that the system what we have considered are linear time invariant, and if the system is linear time invariant, definitely the system can be represented in the form of xt is equal to a into xt plus b into ut, and yt equal to c into xt plus d into ut, and the initial condition x0 is equal to x of 0. So now this set of equations can be represented using block diagram, because sometimes block diagram will give the comfortability to the designer to see that how the system variables are connected to each other. So now I will tell you how to write the how to draw the block diagram representation of this given system, and here you try to understand that all these are not a scalar quantity. So here xt having n number of component, okay, and you can assume that u also having m number of component, means m number of inputs are there, and output yt having p number of components, means p number of outputs are there. So I will tell you, though it is the representation of the system equation what I have shown, but I will tell you, or I will give you the hint how you will actually draw the system representation using block diagram. Once this system is given to you, you should start with the input and you should end with the output. That is the only clue. So now you see, I am showing you the system equation. So we have x dot is equal to a into x plus b into u. I am not writing the argument t. So now we will start with the input. So start with the input u, and u is multiplied with the gain b. Fine. Now it is added. So here one adder we will use. okay, so it is added. Now we have to build the equation of x dot. So we are going to build the x dot. Okay, so x dot require not only b into you require the component a into x. So how we will get the a into x, because only you have the x dot. So if you want to get the x, then you have to integrate to get the x. Once you will get x, then you can multiply with a, gain a, okay, because it is constant. A is constant vector. Okay, now here you can add with this to get the first equation. Okay, that is x dot equal to ax plus bu. Now rest of the things is the output equation. Output equation is what? Y equal to cx plus du. So already you have the x. So if you multiply this x with c, then you will get the cx component, but it has to be added with du component if du is present. So now from u directly you can take and you can multiply with the component d. Okay, and then you can have the du component such that you can get the output y. Fine. And here why we are using thick arrows, because it is representing that it is not a scalar quantity. U is not a scalar quantity, means if you want to say that u is not a scalar quantity, we have u m number of component. Here x having n number of component and y having p number of component. Okay, so which has been shown in the figure what it is represented here. Now where you will give the initial condition? Now to solve the xt you are integrating, so here actually you need the initial condition x of 0 to start the simulation or to implement the circuit. If you want to get the output yt, only the input is not sufficient. You have to define what are the initial condition of the state variables are. So this is very much clear using block diagram representation. Now we will move to an example, and for that example we will try to draw the block diagram, because this is a generalized representation of a given system. Now we will try to learn that if a particular system is given, how to draw the block diagram. But before that, one important thing I want to notify here, that is why we are using integrator while implementing the system using block diagrams, or if I want to do the simulation, then also this block diagram has to be implemented either in computer, or if you want to implement in the laboratory, then using the operational amplifier you can implement this. So now question is, why the integrator we are using? Now that can be understood with this example, that we are not using differentiator, instead of that we are using integrator. Why? Now suppose we have a very small signal which could be representing the noise signal, which having very low magnitude, that is 10 to the power minus 3, and but with high frequency 10 to the power 6. Omega t is 10 to the power 6. Frequency is very high but magnitude is very low. So suppose this signal is present with a measurement signal, that is xt. I told you that for different example, xt could be the voltage, xt could be the position. So now when you are measuring or when you are doing any operation with such signals with the differentiator, then if with such signal some noise signal is added, then the noise signal also will be differentiated along with that variable. So then if you differentiate the noise signal which is having very low magnitude and high frequency, after derivative operation you are finding that its magnitude become 10 to the power 3, means the derivative operation is going to magnify the noise magnitude which is present in the signal. But in comparison to that, if you integrate this noise signal, then you are finding the magnitude become 10 to the power minus 9. So basically the integrator or integrating operation is going to suppress the noise signal. So integration reduces the magnitude of the high frequency disturbances. Hence we use only the integrator, summer or adder and gain amplifier for implementing a differential equation. So here you can see what are the components we are using to implement a set of differential equation. We are using integrator, we are using summer, and we are using gain amplifier, because you see A, C, D, they are the constant matrices. To implement that we require some gain amplifier only. So this is the implementation part, as I mentioned. Now we will see with the examples how we can draw the different block diagram for a given system. Okay, now you see the example, this example at the beginning we have considered, it is a simple RLC circuit. Then if we apply the KVL, then we can write that VCT, the voltage across the capacitor, is equal to the input voltage, that is VST, minus L into DIL by dt. And if we will apply the KCL at this junction, then we can write that ILT is equal to C into dVC by dt plus VCT by R. So now this is the two differential equation we are getting, which is describing the dynamics of the system. So now from this differential equation, actually you can guess what could be the state variables for the system. You can see that we have a differential relation with the variable IL. So IL will one state variable, and you can see in this equation dVC by dt is there. So definitely it is indicating that the voltage across capacitor VCT will qualify as another state variable. Now we can write the input output relation, which is describing the dynamics of the system. That can be written also. So here the input is UT, that is VST, and the output YT is defined by VCT. So once it is defined with these two equations, we can write the second order differential equation, which is describing the dynamics of the system and which is only related with the YT and UT, that is the output and input of the system. Now suppose if we want to represent this circuit in the state space, then what could be the representation? So now first model I am showing, where as our first choice that ILT and VCT are the state variables. So x1t equal to VCT we have taken, and x2t is equal to ILT. So now if you have chosen these are the two state variables, then you have to write dIL by dt and dVCT by dt. So that's why first we have written dx1 by dt, which is basically dVCT by dt. Okay, so that will be written from the equation number 66, that is 1 by RC x1t plus 1 by C into x2t. Okay, very easy to write. And similarly we can write dIL by dt by the next equation, that is by equation this first equation, that is 1 minus 1 by L x1t plus 1 by L into ut. Fine. So now with this we can represent the state space representation of the given system. Now the question is that how we can write or how we can draw the block diagram using this state equation and output equation. That for this example or this model I am going to show you, then rest of the model you can understand how to draw. So first equation you can see dx2 by dt is equal to minus 1 by L into x1 plus 1 by L into ut. As I told you that you have to start with the input. So here single input is there, so I am representing with a single line, that is u of t. Now u of t is multiplied with a gain, that is 1 by L, and it has to be added. Okay, and first equation if you want to get, that is x2 dot require where what, now it is 1 by L into ut, that is in plus minus 1 by L into x1t. So we don't know how to get the x1t now, so just what I'll do with the with a block, I'm assuming that we are getting x1t now and x1t now, and we will multiply that one with 1 by L. Okay, so then we will get x2 dot. So if you integrate it, then definitely you will get x2. Fine. Now you look to construct the x1 dot. What are the things are required? So x1 dot you require minus 1 by rc into x1 plus 1 by c into x2. So now if we will multiply x2 with 1 by c, and then if we took a adder, okay, then we actually trying to construct the x1 dot. So how we will get, now if we integrate, then we will get x1, and to build the x1 dot, what thing you require? Now you require the gain, that is by 1 by rc, and that is I think negative. Here also this 1 by L is negative, so here it is negative. So now 1 by rc has to be multiplied with x1, and also x1 is available, so 1 by L into x1 to get this. So this will be the state variable representation in block diagram for the model 1, and you can understand now this integrator required the information of x20, and this integrator required the initial condition of x10 to start the simulation. Okay, so now we will for the same system we will try to represent it by model 2. You see, for the RLC circuit, what we have considered is represented by this second order equation, and now we will choose another set of state variables. You see, x1t is equal to y, and x2t is equal to y dot. So these are the two state variables we have chosen, y and y dot. Fine. Now if you use y and y dot, and output still it is the voltage across the capacitor, then the first differential equation you will get dx1 by dt equal to x2, because you are finding that x1 dot is equal to y dot and y dot is equal to x2. And what will be the dx2 by dt? Dx2 by dt you are finding that it is basically y double dot. So y double dot from the equation 69, what you can write now, 1 by lc yt is x1t minus 1 by rc y dot means x2 plus 1 by lc into ut. So another representation we will get for the same system, same RLC circuit, whose A, B, C and D matrices like this. And if we want to represent this circuit now using block diagram, then this could be the representation. You see how it is doing. Now first you see dx2 by dt is equal to minus 1 by lc into x1 minus 1 by rc into x2. Okay, so this is your y dot is equal to basically representing what, that is x2, and this is basically representing x1. And now x1 into 1 by lc, then 1 by rc into x2, then we are getting the y double dot along with the input u into 1 by lc. So this will be the block diagram representation of the state variable representation of this system. Again we will move to the third representation of the system. Same, you see, same differential equation, but now what I will do, I will choose the state variable x1t equal to y and x2t equal to y dot plus 1 by RC into y. So here you see always the choice of state variable do not have the physical meaning. You see x2 do not have any physical meaning because y dot plus 1 by RC into y. So it is a combination of voltage and current you are taking. So always the choice of state variables does not mean that it will be always the physical variables. Previously for the mechanical system, only the mass example what we have taken, you at that time you can remember that Z1 and Z2 was the combination of the velocity and the position of the mass. So it do not have any physical meaning. So always the choice of state variables may not have the physical meaning, but the choice of state variable actually depends on the particular design. So that definitely when the event will come, we will discuss. So now x1 is equal to y and x2 equal to y dot plus 1 by RC. These are the two state variable has been defined, and now you have to represent the system, the same system using these two state variables. How we will do? Now first I will try to write x1 dot. What is x1 dot? That is y dot. So x1 dot we are finding x1 dot is equal to y dot. And from the equation, from this expression, we can write that y dot is equal to, that is x2 minus 1 by RC into y. Y means what? That is x1. So first equation, that's why you see dx1 by dt is y dot, that is minus 1 by RC x1 plus x2. Similarly, if I want to write the x2 dot, it is y double dot plus 1 by RC into y dot. From where I will get the y double dot? From the main equation, that is 1 minus 1 by RC y dot minus 1 by LC y plus 1 by LC into UT plus y 1 plus RC y dot. Now you are finding that these two factors are cancelled out, so we will leave with minus 1 by LC into x1 plus 1 by LC into UT. So now using these two equation, this equation and this equation, we can represent the state space representation of the given system in the following form. Now you see the A, B, C matrices are different from the model 1 and model 2. And now if we want to represent this state equation using block diagram, the block diagram representation will be like this. And you see for the same differential equation, we are going to get a different representation of the system. Why this has happened? Because we have chosen different set of state variables from the earlier one. And now I'm going to show you for the same RLC circuit what will be the model 4. So same differential equation. Now it has been told that the state variables are x1t equal to y, x2t equal to y dot, and x3 equal to y dot plus 1 by RC into y. So now a dummy state variable has been appended with the state variables x1t and x2t, and if you write x1 dot, x2 dot and x3 dot, then the equations will be like this. Now if you represent the same differential equation, then you are getting the block diagram representation like this, along with a model which is third order model you are getting. So here very interesting thing you have to notice. Though we have a second order differential equation, by choosing a set of state variables which are x1t, x2t and x3t, the same second order differential equation can be represented using third order state space model. So here many things are to be pointed out. First thing is that by looking the A matrix, suppose the A matrix dimension is 3 by 3, and if we conclude that the order of the system is 3, that could be wrong for few moments. Okay, so it is not all the time that if the dimension of A matrix is 3 by 3, then the system order will be 3. It is wrong. So to determine the order of the system, better we have to see the characteristics equation of the system, or the input output relation which is described by the dynamics of the dynamical equation, that is differential equation, that we have to see. You see, for all the model 1, 2, 3 and 4 we have derived, for all the model the differential equation is not going to change. And if you find out the characteristics equation, what will be that? That will be s square plus 1 by rc plus 1 by LC is equal to 0. So that will be the characteristics equation. It can be proved that for all these models, model 1, model 2, model 3, model 4, for the same system, the characteristics equation is same, transfer function is same. But at this moment, we don't know how to represent the, or how to find out the transfer function and characteristics equation from the given state space equation. That mechanism we don't know. That's why I'm not able to show you. But in later point of time, when we will come to know that from the state space equation, how can we find out the characteristics equation, and how can we find out the transfer function, then we can verify even the for the same system we are getting different model, but their intrinsic characteristics described by the differential equation, or by the characteristics equation, or by the transfer function will be same. So here multiple things we have understood from this example, that is for the RLC circuit, that several state variables can be chosen, and if the several state variable can be chosen, several model can be created, but for all this model you will find that the characteristics equation and the transfer function will be same. And also it is if you decide to look the A matrix, by looking the A matrix about the order of the system, then it might be wrong, because we have found that though we have represented the system in third order differential equation, but practically the system is second order. So by looking the A matrix dimension, we should not decide about the order of the system. Better to decide the order of the system, we look the characteristics equation of the system. Fine. So now these are the facts. Again, we are going to summarize that given a system model, how many state variables? The number of state variables are equal to the initial conditions required to describe the initial energy stored in the system. So here in this example, you will find that two energy storing elements are there. What are they? They are the inductor and the capacitor. So at least two state variables will be there. That is the voltage across the capacitor and current through the inductor. Okay. Now another point is that assign a state variable to every variable that has its derivative represented in the equation of motion or dynamics. So that is another clue to choose the state variables. Even if you are not able to know by looking the system, then what you will do, you will write the differential equations of the system. Once you will write the differential equations of the system, then you have to see the state variable to every variable that has its derivative represented in the equation of motion and dynamics. So then easily you can identify who are the state variables in a given system. And remember, the choice of state variables are not unique for a dynamical system. The state space representation is also not unique for a dynamical system. But the input output relation or the transfer function described by the differential equation is unique. And at this moment our claim is that if you able to represent the any system in the form of x dot equal to ax plus bu, y equal to cx plus du, where a, b, c, d are constant and do not depend on the time t, then definitely this system is, or we are representing a system which is linear and time invariant. But this claim definitely we will prove that if for any system, if you are writing in the form of x dot equal to ax plus bu, y equal to cx plus d, where a, b, c and d are constants, Constants means the elements of these matrices are constant, which do not depend on t, so definitely it is a linear time invariant system. So I will stop here, and next class I will come with an example of nonlinear system, and we will come to know that how we can represent a nonlinear system using state space. Thank you.